Guys, here's your video for today. It won't be that long, and then you can get started on your homework because bad me, did not put your homework in Google Classroom until late last night. So here's your warm-up. So go ahead, try this problem. Pause the video right now, do the problem, and then unpause it, and I'll show you the solution. So the solution to this problem, I would have used the formulas. So they told you the probability of D is 0.6 and the probability of D and E is 0.18. So they also told you that D and E are independent. So because of that, I know that the probability of D and E would be equal to the probability of D times the probability of E, because of independence, right? If those weren't independent, then I couldn't do this. But because they are independent, I can. And we know that this is 0.18. We know this is 0.6. And you just need to figure out what that one is using your algebra. So I think everyone can figure out what it is. 0.6 times something is going to be 0.18. So probability of E must be 0.3. We're going to use this in the next part. So I look at my answer choices. Oh, they don't say, nope, those are not them. So not going to be one of those. So then I notice all the other ones are asking for D or E. So using our formula, we know the probability of D or E is always going to be the probability of D plus the probability of E minus the probability of the overlap, which is the and D and E. So what do we know? Well, we know D is 0.6. We know E is 0.3. And we know that D and E was 0.18. So we actually know everything in there. So you go ahead and work that out. And when you work that out, you get 0.72. So the correct answer should have been D, 0.72. So that's how I would have done that problem instead of a Venn diagram. You could have done it with a Venn, but I feel like since they defined everything and they had all the variables, it would have been easy with the formulas rather than a Venn diagram. If you did do it with a Venn, here's a real quick Venn so you can check your Venn diagram. I would have had D, I would have had E, and what we knew at the beginning was we knew this whole circle is 0.6. We know the middle here is 0.18, and that's all we knew. So then you'd have to use the independence aspect to figure out, oh, this whole circle must be 0.3. And then using your subtraction, you figure out that this, I think, was 0.42, and this one over here should be 0.12. And then if you add up the stuff that's inside the circles, you end up getting 0.72 for D or E. So that would have also given you letter choice D. So either way works, whatever way you like, that's the way I want you to use. That was a good little warm-up. I've seen that on multiple choice. Okay, the new problem. So yesterday we did the problem where we found, let me close this, it's slowing down my computer. Okay, where we found the percentage of bottles that were spoiled, right? We had to do this branch because it could have came from machine A, or it could have came from machine B, so we did the B branch and the A branch, and then we added them together, and that gave us the probability that we get a spoiled bottle. We're going to do the same thing today, but we're going to add a special wrinkle to the question. So the new question today is this part right here you're going to see. So a recent Maryland highway safety study said that in 77% of all accidents, the driver wore a seatbelt. Okay, 92% of accidents, they escaped serious injury, and 63% non-belted drivers escape serious injury. So you need to realize that this is a tree diagram, not a Venn diagram. How do I know that? That's always the first question students ask me is, how did you know this was a tree? I know it's a tree because there's two things happening. You either wear your seatbelt or you don't. And then the next thing that happens is you either get injured or you don't. So when I read this question, I noticed it was all about wearing seatbelts and then whether you got injured. Those are two events. So when you see two events come up, you know you're doing a compound event. That's when I run to a tree diagram. So on my tree diagram, my first branch would be whether I wear a seatbelt or I don't wear a seatbelt, right? That's the first level. And then the second level is whether I get injured, seriously injured, or not. Whether I get injured or die, I guess, or not. So, they have given you probabilities. They said that in their recent study, 77% of accidents, the driver was wearing a seatbelt. So 77% of accidents, drivers wore seatbelts. That means that in 23% of accidents, they do not wear seatbelts because those add up to 1. Okay? Make sure my math's good. Sounds good. Now, of people wearing seatbelts, 92% escaped serious injury. So 92% of the wearing seatbelt people did not get very hurt, and 8% got very hurt. But in the other group, 63% were so fortunate to escape injury. So in the other group, 63% escaped injury, but that means that a lot of people got injured here. 37% got injured then. Okay, so our tree is filled out. 2 levels, all the probabilities are on there. Notice this is dependent, because your chance of getting hurt is totally different if you wear a seatbelt or you don't wear a seatbelt. So obviously, these two variables are dependent. If you wear a seatbelt, it causes you not to get hurt as much. So they're asking you for the probability that a driver who was seriously injured wasn't wearing a seatbelt. So they're asking you to figure out the probability that someone wasn't wearing a seatbelt given they got injured. That was what they asked you in that sentence. I know it is hard because you don't see a given in the sentence right there. Okay, there's nothing that says given. Okay, they said, what's the probability that a driver who was seriously injured? So they're not asking you the probability that they were injured. We already know they're seriously injured. Who was seriously injured? So we know they're injured. What's the probability they weren't wearing a seatbelt? Okay, that's what we're trying to calculate. When you do a problem like this with a conditional probability, the first thing you need to do is calculate the probability of the given. So the first thing I need to do is calculate the probability of just getting injured. Okay, that's first, just like we did on that problem yesterday with the bottles. Okay, so probability of getting injured. Well, I could have got injured if I wore my seatbelt and did that route. I could have also got injured if I didn't wear my seatbelt using that route. So the chance of getting injured would be 0.77 times 0.08 for that branch. The chance of getting injured on this branch, 0.23 times 0.37. So I go ahead and use my calculator and calculate those out. 0.77 times 0.08. So there's a 0.0616 chance you get injured on that one. And on the other one, a little higher, 0.0851. You get injured on that branch. So the probability of getting injured is going to be 0.0616 plus 0.0851, right? You add up the two branches for getting injured, and that's your probability of getting injured. I get 0.1467. There's a 14% chance we get injured. I put it in a cloud, okay? We're saving it for later. It's in the cloud. So 0.1467 is our probability of getting hurt. They're asking you basically which of those branches came from the people not wearing seatbelts. Well, the people not wearing seatbelts were this one. That's the part that came from the people not wearing seatbelts. So, to calculate the probability that they just gave you, all you do is put the branch that came from the one you wanted divided by the total of the given. The given is the bottom, right? The given is always the bottom number. And the top number is which one of these branches were the one that you want. We want to know the chance you came from that not wearing seatbelts. So this is the one that came from the branch we want. So when you calculate 0.0851 divided by 0.1467, the chance that someone was not wearing their seatbelt, if we know they were injured, was about a 58% chance. That is the answer. There's about a 58% chance, if we already know that you're hurt when we show up to an accident, that you weren't wearing your seatbelt. You're going backwards sort of on this tree diagram. This is the amount of people that weren't wearing seatbelts in the accident injury group out of the total injury group of 0.1467. It's an extra wrinkle that we're adding, okay? So we add this extra wrinkle. We do the adding, we figure out the two branches, we add them up, we get the total. That will always be the bottom number. When you go over to the formula, that is always going to be the bottom number. And then the top number will be which one came from the branch you want. Oh, 0.0851 is from the branch I'm being asked about. Boom. That's it. That's how you do those problems. They're called Bayes theorems. If you ever want to look up more, it's called Bayes theorem. Okay. They're fun. They're sort of fun, and they're sort of different. People that don't do probability, they don't know where the heck I got that 58%. They're like, how do you go backwards? I thought only 23% were not wearing seatbelts. Yeah, but we know you're not. We know you're injured. So that's changing when we're looking backwards at it. We're looking from the injured part. So it changes everything. Okay, so that's a tough problem. Totally admit that's a tough problem. Okay, it's supposed to be tough. That's why I saved it for the end. So I'm going to give you a real world example of this problem. Right, this is one that they made up. Great, fine, I could do it. It's not fun though. I want something fun. So here is your fun problem that I just made up. Okay. I was thinking about getting a COVID antibody test. Thinking about getting one. Like, I don't think I've had COVID, but I don't know. Okay, right? If I was didn't really get many symptoms and was asymptomatic, maybe I did have it at some time last year. I think a few of my students had it last year in like February and March before we got out of school. I had one student was out for 2 weeks, got pneumonia. I wonder about that one. And then I have another student whose dad went to Japan and he came back to school super sick and he had pneumonia too. I wonder about that one. So you never know. I could have been exposed before we started testing people. So I wonder if I have had COVID. So I could go get an antibody test, right? They'll do a blood test on me. They'll figure out if I have COVID antibodies in my blood. Those tests are about 93% accurate. So that means they'll be right about 93% of the time. Okay. I want to know what is the probability that I actually had COVID if I go and I get a positive test, right? I'm sort of going backwards. I'm saying if I get a positive test, what's the probability I actually had COVID? Okay, most people will say 93%. It's not 93%. Okay, it isn't. Okay, so this is a tree diagram because you have two events. You either had COVID or you didn't, and then you either get a positive test or you don't. So there are two things happening here. So my first level is I either had COVID or I didn't. So I'll put COVID or not, right? That's the first level of my tree. The second level of my tree, I go get an antibody test, and I test positive, or I test negative on my antibodies. I could also have been here, right? Didn't have it, but I could test positive, or I could test negative on my antibodies. Okay, so there's the tree of everything that can happen. Let me put in the probabilities. There is I'm estimating about a 5% chance we've had COVID, right? The COVID has still not been in our population long enough to have that high of an incidence. So there's still probably only about a 5% incident rate. So about 5% of people probably have had COVID. Maybe we're getting to 10, but I'm going to say it's about 5%, which means 95% of people have not had COVID. And for positive tests and negative tests, well, 5% have had COVID. Let's see, it's 93% accurate. So if I had COVID, actually, I should get a positive test. So that the 93% would go there on the positive branch because that's the right answer for where I'm at, which means I will get a wrong answer 7% of the time. We will show that we're negative and we actually did have COVID. And then for the not having COVID, if you didn't have it, I should get a negative test. That would be accurate 93% of the time, but there are some times where I will get a wrong test, right? I will get a positive and I actually didn't have it. That would be 7% of the time. So you got to think about when they say 93% accurate, which one it goes on, because it depends on whether you had COVID or not, what the positive part was. So the probability that I'm asking you to figure out is the probability that you actually had COVID given that you get a positive antibody test. Okay, so first thing we need to calculate, how many positive tests do we get? So that's first thing I need to calculate. What's the probability of getting a positive test? Okay, so one way to get a positive test is this branch. The other way to get a positive test is that branch. So positive test on the top one would be 0.05 times 0.93. Positive test on this one would be 0.95 times 0.07. So let's see what we get. 0.05 times 0.93. I'm getting 0.0465 to get a positive test up there. And on the bottom one, 0.95 times 0.07. I'm getting 0.0665. Okay, so we have about a 6% chance to get a positive test on that branch. So the chance that we get a positive test is 4% plus the 6%. So when we add those two together, we end up getting about 11% chance. So there, when you go in and just take a random antibody test, I'm going to have about 11% chance to get a positive one. When I just go in randomly, not knowing if I had it or not, about 11% chance to get a positive antibody test. Okay, not a PCR test. This is an antibody test that you do after you've had the disease. It's about 11% chance. So what's the probability that I came from COVID, that I actually have COVID? So the probability that I actually have COVID given that I get a positive test is going to be the probability of getting a positive test, 0.113, there's the bottom. And which one came from the COVID branch? It's the top one that came from COVID. So about 0.0465. So 0.0465 divided by 0.113 and that gives me a probability of 0.4115. So this is going to blow your mind. The chance that you actually had COVID, if you get a positive test right now in a lab, is actually only 41%. There's actually only a 41% chance that I actually really had COVID, which makes that test seem like, what the heck is the point of an antibody test? If there's still a 41% chance, there's only a 41% chance I actually really had it. There's a 60% chance that I didn't have it, even if I get a positive test. Okay, that one is way bigger than that one. Okay, so how do we fix that? How do we make the test do a better job? Well, we can make the test more accurate. Okay, maybe 93 is not good enough. Maybe you need to be 99. Change that to 99%. That would change that to 0.01. That might change it, right? That's one way to do it. Another way to do it is to have more people have COVID in our real society. If more than 5% of people have had COVID, right, maybe this is 10% of people now have had COVID. So if that's 10%, that's 90%, right? These numbers will change a little bit. So then this will be a little bit higher. But yeah, it's crazy to think about. Most people don't think about it. They think that the probability that you actually have COVID, if you get a positive test, is the 93%, but it's not the 93% because it all depends on the prevalence rate of COVID in our society. That's what it depends on. We have so many people that haven't had COVID yet that even though there's a small rate of getting positives out of that group, it ends up being a really big group because we have so many people in that group. Even though 7% of that group is still big compared to that group. So it's weird, okay? But mind-blowing right there. Mind blown. Okay, you guys, so that's 20 minutes. That was all I wanted to do today. So you do that, went over those, go for your homework. I have your homework in there now on Google Classroom. I put it in late last night. The rest of class right now, I want you to do homework. That gives you about an hour to do your homework right now in class. Then hopefully you don't have to do it outside of class. So that's what my goal is, give you a little break, let you do it during class. You don't have to do it later. So have a good day. I'll be around after school. If you send me an email, I'll be on here. So send me an email if you want to come ask me some questions or you want to show up. I can set up a Zoom, right? The office hours Zoom, and you can come in. So we'll see you guys later. Have a good day.